All right, we're about to dive into a pretty radical idea today. We're going to explore a theory that suggests gravity, well, it isn't what we've always thought it was. We're looking at a framework that proposes gravity literally emerges from the fabric of empty space. This is dynamic vacuum field theory, or DVFT for short. The entire theory really boils down to this one single provocative question. What if we've been looking at it all wrong? Instead of the vacuum being this empty, passive nothingness, imagine it's actually a dynamic, active medium. And if that's true, what if gravity is just a consequence of that medium's behavior? That's the core idea we're going to unpack.
So how in the world do you model an active vacuum? Well, DVFT treats it as a complex scalar field. And this isn't just some mathematical sleight of hand. The model gives the vacuum real physical properties, and it's these properties that can actually generate the forces we see all around us.
And here is the central mechanism. In this model, what we perceive as gravity is really just an effect caused by gradients, changes in the density of this vacuum field. What's so cool about this is that it acts as a bridge. It connects the super complex, full relativistic theory to a much simpler Newtonian version that we can actually use to test against real astrophysical data.
Okay, to see how this all really works, we got to pop the hood and look at the mathematical blueprint of the theory. Let's dig into the core equations that really govern the behavior of this whole dynamic vacuum idea. Right at the heart of the theory is this thing, the complex scalar field, which we call phi. You can think of it as having two main jobs. First, there's its amplitude, ρv, which basically represents the vacuum's density. And second, there's its phase, theta, which describes its coherence. Everything else that happens emerges from the way these two properties play together. And here it is. This is the equation that defines that vacuum field at every single point in space-time. It so elegantly combines the amplitude, ρv, with the phase, theta. All the complex dynamics we're talking about, they all come from how these two components behave and interact with each other.
And this is the master blueprint, the total action. Now, for anyone who's worked with field theory, this is going to look pretty familiar. It's got three key parts. The R term for space-time curvature, straight out of general relativity, Lm for all the standard matter we know and love, and then there's the crucial new piece, L phi, which describes the vacuum field itself. Essentially, this one equation contains all the physics of the entire system.
Now, trying to work with that full theory is, well, it's a beast. It's incredibly complex. So to connect it to the real world, like how stars are moving around in a galaxy, we need to make a really important simplification. And that's where the weak field approximation comes in. This table really shows you the key assumptions we make. To simplify, we assume space-time is nearly flat. But the most critical step is what we do with the phase, that theta term. We basically treat it as a constant, which means its dynamics are frozen out of the picture. And that leaves only the amplitude, ρv, to drive all the physics we're interested in at these scales. So after making that approximation, what pops out is a modified version of the good old Poisson equation. But look closely at the source term on the right side. The potential, U, isn't just sourced by matter density ρm anymore, it's now sourced by both matter and the vacuum's own density ρv. This is a huge shift in how we think about what generates gravity. Okay, so with that simplified equation in our back pocket, we are now ready for the main event, actually deriving the formula for gravity directly from the properties of the vacuum itself. This brings us to the absolutely critical question. We know that ρv acts as a source for the potential U, but is there a more direct, a more fundamental link between the two? The answer, it turns out, is yes, and it's the key to this whole thing. And here it is. This is that key insight. The potential, V, is proportional to the natural log of the vacuum density. This deep connection basically comes from the way the vacuum medium itself responds when matter is present, which effectively changes the local fabric of space. And this brings us to the hero equation of this entire derivation. Since we know gravitational acceleration, g, is just the negative gradient of the potential u, we can take the gradient of our new expression for u. What we get is this incredibly simple, incredibly powerful formula. G equals negative c squared times the gradient of the natural log of the vacuum density. Gravity is literally just a measure of how steeply the vacuum's density is changing from one place to another. So we have this really elegant theoretical result. It's beautiful on paper, but does it have anything to do with reality?
To find out, we have to test it against one of the biggest, most stubborn puzzles in all of astrophysics, the way galaxies rotate.
So the challenge is this long-standing mystery of flat rotation curves. Stars way out on the edges of galaxies are moving way faster than they should be based on all the visible matter we can see. The standard explanation for this is a giant halo of unseen dark matter. But DVFT offers a totally different idea. What if this extra acceleration is just caused by a gradient in the vacuum itself?
So how do we actually test this? It's a pretty straightforward four-step process. First, we just take the observed acceleration from a galaxy's rotation curve. Second, we set that equal to our new formula for gravity. Third, we integrate that equation to solve for the vacuum density profile ρv. And that last step tells us exactly what the vacuum density has to look like to create the rotation we're actually seeing.
And this is the solution that pops out of the math. The theory predicts that the vacuum density must follow this very specific power law relationship, dropping off smoothly as you move away from the galaxy's center. And the exact steepness of that drop, that little exponent a, is determined by the galaxy's own rotation speed.
So, what's the verdict? Well, this derived profile is a perfect match. It is precisely what's needed to explain those flat rotation curves without invoking a single bit of dark matter. A theory that started with these abstract principles makes a concrete prediction, and that prediction aligns with observation. That is a really powerful piece of validation for this whole framework.
And so we're left with this final, really tantalizing question. If gradients in the vacuum can successfully explain how galaxies rotate, what else could this dynamic vacuum be responsible for? Could it also explain things like gravitational lensing, or maybe even the accelerated expansion of the entire universe? This theory really opens up a completely new way of looking at the cosmos.